Hello and welcome. In this video, we're going to be looking at a further Pure Maths 1 paper, that's 9231/12 from October-November 2020. So let's get right into it. We're starting with question number 1, which says the cubic equation x cubed plus bx squared plus cx plus d equal to 0, where b, c, and d are constants, has roots alpha, beta, gamma. It is given that alpha, beta, gamma is equal to -1. State the value of d. Alright, so for this particular question, considering this cubic equation we have been given, we can say that the sum of roots is going to be minus b. So that's minus b. The sum of product of pairs, in this case, is going to be c. And the product of roots, alpha, beta, gamma, will be represented by minus d. So that's what we have. Now, we have also been given that alpha, beta, gamma is equal to -1. And we also established that alpha, beta, gamma is equal to minus d. So basically that means that minus d is equal to -1. So d is equal to 1. Let's go on to part B. It says, find a cubic equation with coefficients in terms of b and c, whose roots are alpha plus 1, beta plus 1, and gamma plus 1. Alright, so in this particular case, we're going to use substitution. I'm going to say let y be equal to x plus 1, which will lead us to having x being equal to y minus 1. So we're going to substitute x into the equation. Alright, so if we do that, it means we'll be having our equation as x cubed, which is y minus 1 cubed, and that's plus b of x squared, which is y minus 1 squared, and that's plus cx, so that's c of y minus 1, and it's plus d equal to 0. So that's what we have right here. And what we're going to do is now expand the brackets and see what it simplifies to. So expanding y minus 1 cubed should give us y cubed plus 3 choose 1 of y squared of minus 1 plus 3 choose 2 of y of minus 1 squared of minus 1 cubed. And that's going to be plus. Now on this part, that's gonna give us b of y squared minus 2y plus 1, and that's plus c of y minus 1 plus d equal to 0. So basically we have y cubed minus 3y squared, and that's plus 3y minus 1 plus, now expanding this part, we get by squared minus 2by plus b plus cy minus c plus d equal to 0. Now grouping the terms, for the terms in y cubed, we only have y cubed. And now for the terms in y squared, we have minus 3y squared plus by squared. So we have, I'll write that as b minus 3 of y squared, factoring out the y squared. For the terms in y, we have 3y minus 2by plus cy. So I'll factor out the y, which means that we'll be having 3 minus 2b plus c of y. And lastly, for the constants, we have minus 1 plus b minus c plus d. Now remember, we had gotten d to be 1. So essentially we have 1 right here. So I'm going to place a 1 here. So when we say minus 1 plus 1, we get 0. So what we're left with for the constants is b minus c. So that's going to be plus b minus c equal to 0. Okay, so this is what we have for the equation. That's the cubic equation that they want us to find. Okay, so that's the answer here. Let's move on to the next part. On part C, the question says, given also that gamma plus 1 is equal to minus alpha minus 1. Deduce that c minus 2b plus 3 of b minus 3 is equal to b minus c. Alright. Now, we're going to make use of the equation we got right above. Okay, so this one here. And I'm going to paste it down here. So this is the equation we got right above. That's the equation which is in terms of y. So for this equation, the roots are alpha plus 1, beta plus 1, gamma plus 1. So we're going to start by finding the sum of roots. Okay, from this equation, we have the sum of roots as being minus of the coefficient of y squared over the coefficient of y cubed, which is 1. So basically, we have minus of b minus 3 being equal to the sum of roots, which is alpha plus 1 plus beta plus 1 plus gamma plus 1. Now, we have been given that gamma plus 1 is minus alpha minus 1, which is the same as gamma plus 1 is equal to minus of alpha plus 1. So, with what we have, we can say minus of b minus 3 is equal to alpha plus 1 plus beta plus 1. But for gamma plus 1, we can use minus of alpha plus 1. So these two will add up together and give us 0. So we are left with beta plus 1 is equal to minus of b minus 3. So that's what we have in right there. The product or sum of product of pairs from the equation, that's the coefficient of y over the coefficient of y cubed. Okay, so in our case, that's 3 minus 2b plus c, and that should be equal to, when we talk of sum of product of pairs, that's like alpha plus 1 of beta plus 1 plus beta plus 1 of gamma plus 1 plus alpha plus 1 of gamma plus 1. But again, we're using the result that gamma plus 1 is minus of alpha plus 1. So that's like alpha plus 1 of beta plus 1 plus, and for here, substituting, we should get minus of alpha plus 1 of beta plus 1. Okay, so I've substituted gamma plus 1 with minus of alpha plus 1. That's going to be plus, again here, where there's gamma plus 1, we will put minus of alpha plus 1. So that's going to be minus of alpha plus 1 squared. So that's all equal to 3 minus 2b plus c. Now, adding up this 2 give us 0. So we are left with minus of alpha plus 1 squared is equal to 3 minus 2b plus c. So let's leave this result like that. Okay, so this is what we got for the sum of roots. This is what we got for the sum of products of pairs. Lastly, let's talk about the product of roots. For the product of roots, this is going to be minus of the constant over the coefficient of y cubed. So that's minus of b minus c. And that's equal to the product of the roots, which is alpha plus 1, beta plus 1, and gamma plus 1. Now, we are using the result that gamma plus 1 is minus of alpha plus 1. So it's as good as we have alpha plus 1 of beta plus 1 of minus, put a minus, of alpha plus 1. So that's all equal to minus b minus c. So it's like we have minus of alpha plus 1 squared of beta plus 1 being equal to minus of b minus c. So minus of b minus c, like this. Now, we have these three results, and we're going to make use of the third result, okay? So I'm going to say, therefore, on the third result, we have minus of alpha plus 1 squared here. And for this, we got that to be equal to 3 minus 2b plus c. So it's like we have 3 minus 2b plus c. And we also have beta plus 1. And beta plus 1, we'd actually gotten that to be minus of b minus 3. So we have minus here of b minus 3. And that's equal to minus of b minus c. So eventually we have 3 minus 2b plus c of b minus 3 being equal to b minus c. And this result is what they want us to show. Okay, right on here. So that's what we have deduced. So what we have here is the answer. Let's move on to the next question. On number 2, the question says, prove by mathematical induction that 7 to the 2n minus 1 is divisible by 12 for every positive integer n. Alright, so I am going to start by proving for n is equal to 1. So for n is equal to 1, we can say 7 to the 2 of 1 minus 1 gives us 49 minus 1, which is 48. And 48 is indeed divisible by 12. Therefore, it's true for n is equal to 1. Then I'm going to assume true for n being equal to k. So if n is equal to k, it means that 7 to the 2k minus 1 should be divisible by 12. So it has to be equal to 12l, which represents a multiple of 12. Essentially, it means that 7 to the 2k minus 1 is divisible by 12. Now, we're going to prove for n being equal to k plus 1. We are going to say 7 to the 2 of k plus 1 minus 1, okay, which is equal to 7 to the 2k plus 2 minus 1, and that's equal to 7 to the 2k of 7 squared minus 1. That's like 49 of 7 to the 2k minus 1. That's like 48 plus 1 of 7 to the 2k minus 1. That's like 48 of 7 to the 2k plus 7 to the 2k, I'm just expanding brackets, minus 1. So I multiplied the 7 to the 2k into the bracket to get these two terms. Alright. Now, we have 48 of 7 to the 2k, but if you look at this part, we can now make use of the assumption to say 7 to the 2k minus 1 is 12l. So we have here plus 12l. Alright. So if I let m be equal to 7 to the 2k, it therefore means that what we have is 48m plus 12l, which is clearly divisible by 12. If we factor out 12, we get 4m plus l. So that's clearly divisible by 12. So therefore, the statement is true for n being equal to k plus 1. Alright. So if that is so, we can therefore write down the conclusion that if true for n is equal to k, it means that it is also true for n is equal to k plus 1, and therefore by the principle of mathematical induction, it has to be true for every positive integer n. So that's how we answered this particular question. Let's go on to number 3. On number 3, they say by simplifying x to the n minus root of x to the 2n plus 1 of x to the n plus root of x to the 2n plus 1, show that 1 over x to the n minus root of x to the 2n plus 1 is equal to minus of x to the n minus root of x to the 2n plus 1. Alright. So with what we have been given, if you look at this thing that we have here, we can multiply numerator and denominator by the conjugate of the denominator. So essentially, we will be having 1 over x to the n minus the square root of x to the 2n plus 1 multiplied by x to the n plus root of x to the 2n plus 1 over x to the n plus root of x to the 2n plus 1. And when we do that, we'll be having on top x to the n plus root of x to the 2n plus 1, and that's over x to the, because these two are like a difference of 2 squares, so it's x to the 2n minus, if we square these, we get x to the 2n plus 1. Alright, so essentially this will give us on top x to the n plus the square root of x to the 2n plus 1, and it's over the denominator here simplified gives us minus 1, which will then result in us having minus of x to the n minus the square root of x to the 2n plus 1. And that's what they want us to show here. So I'll say here shown. Let's go on to part B, where they say let u sub n be equal to this thing given. Alright, use the method of differences to find the sum to n of u sub n in terms of capital N and x. Alright, so in this particular case, we are looking for the sum to n, okay, of terms of the form u sub n, and that's going to be equal to the sum from n is equal to 1 up to n of u sub n is equal to this thing here. So we have x to the n plus 1 plus the square root, and that's the square root of x to the 2n plus 2 plus 1. And for this thing that we have here, this fraction, we had shown that it is actually equal to this. So we're going to say minus x to the n minus the square root of x to the 2n plus 1. So this whole thing is under summation. So we are going to now list down the terms, okay, starting with when n is equal to 1. When n is equal to 1, we will be having x to the 2 plus the square root of, here becomes x to the power of 4 plus 1, and that's going to be minus x, that's going to be minus again of the square root of x squared plus 1. So that's going to be plus, and now we do for when n is equal to 2, and we're substituting therefore 2 for n into this whole thing. So that means that we'll be having x to the power of 3 plus the square root of x to the power of 6 plus 1 minus x to the power of 2 minus the square root of x to the power of 4 plus 1. We are going to do again for when n is equal to 3, and substituting 3 for n into this whole thing, we get x to the power of 4, and that's plus the square root of x to the power of 8 plus 1 minus x to the power of 3, and that's minus the square root of x to the power of 6 plus 1. So this is what we have in here. So this is going to go on and on and on until we reach the very last term. That's when x is equal to capital N, which will give us x to the power of n plus 1 plus the square root of x to the power of 2n plus 2 plus 1 minus x to the n minus the square root of x to the 2n plus 1. So this is what we're having. Alright, now you can see that x squared adds up to minus x squared to give us 0. X to the power 4 plus 1 under square root minus this also add up to give us 0. So this adds up to this to give us 0, and also this term minus this term give us 0. So all these terms will add up to each other to give us 0, and so will this term and this term be added with other terms to give us 0. Alright, so what remains are minus x minus root of x squared plus 1 and x to the n plus 1 plus root of x to the 2n plus 2 plus 1. So we are saying that this therefore gives us, I'll start with these two, x to the n plus 1 plus the square root of x to the 2n plus 2 plus 1, and that's minus x minus the square root of x squared plus 1. So this is what we get for our answer right here. Let's go on to part C. On part C they say, deduce the set of values of x for which the infinite series u sub 1 plus u sub 2 plus u sub 3 and so on is convergent, and give the sum to infinity when this exists. Alright, now in this particular case we are looking at the infinite series u sub 1 plus u sub 2 plus u sub 3 and so on to infinity, and this can be written in summation notation as the sum from n is equal to 1, okay, up to infinity of terms of the form u sub r. And we had earlier established that if we do the sum to n of terms in this series, we get this result. So we can say here that what we have here, the sum to infinity, is the same as the limit as n approaches infinity of terms of the form of this form here. So x to the n plus 1 plus the square root of x to the 2n plus 2 plus 1 minus x minus the square root of x squared plus 1. Alright, now to answer the first question where they say we should deduce the set of values of x for which the series is convergent. For this series to be convergent, it means that it has to approach a finite value. And for it to approach a finite value, it means we have to consider a set of values of x that will make terms of the form x to the power n plus 1 become zeros. So you need to understand that for values of x between minus 1 and 1, x to the power n plus 1 will approach 0 as n approaches infinity. So with that will mean that this becomes 0 and this part 2 will tend towards 0, so that if that is so, it therefore means that the series becomes convergent. And since the question says we should give the sum to infinity when this exists, it therefore means that the sum to infinity, alright, will be equal to the limit that we get here, which will be, here we get a 1, so 1 and this whole thing minus x minus the square root of x squared plus 1. So that's the answer to this particular question. Let's move on to the next one. Now on number 4, the question says, matrices A and B are given by A is equal to 0, 1, 1, 0, and B is equal to half minus half root 3, half root 3 and a half. So on part A, give full details of the geometrical transformation in the xy plane represented by A. Alright, so if you look at A, alright, you can consider x's, x and y, and an original point 1, 0. So 1, 0, that point is being transformed to these, it's being transformed to 0, 1. Okay, so 0, 1 is this point, that's the point 0, 1. Alright, so that's the transformation going. 1, 0 is the object, it becomes the image 0, 1. Okay, so it could be a reflection going on or a rotation. Again, we can look at the point, another point, the point 0, 1 itself. The point 0, 1 is being transformed onto this column 1, 0, which means this point is going on and is giving us this as the image. So what I can see happening here is a reflection. It is actually a reflection in the line y is equal to x. This line is the line y is equal to x. So that is what's causing this point to be reflected to become this point, and this point to be reflected to give us this as the image. So that's basically what's happening here. Let's go on to part B. On part B, they say, give full details of the geometrical transformation in the xy plane represented by B. Right, so for B, we can see that, okay, if I can have a little sketch to see what's going on here. Alright, so we have the x-axis and the y-axis, the origin here. If we take a point 1, 0, the point 1, 0 is being transformed onto the point half and half root 3. So it's giving us half and half root 3. So maybe somewhere here. Okay, this is half and half root 3. And there's an angle alpha here. Alright, so apparently we can actually see that it's a rotation going on with an angle alpha. And if we make a little right angle triangle, alpha is going to be arctan of half root 3 over half, which is just root 3, which gives us 60 degrees. So I can see here that we have a rotation, and it is a rotation with the center being the origin and by 60 degrees anti-clockwise. So that's the transformation going on for part B. On part C, they say triangle DEF is transformed by AB onto triangle PQR. Show that the triangles DEF and PQR have the same area. Alright, so let's start with the matrix AB itself. AB is the product of A and B. So 0, 1, 1, 0. And this other matrix, half minus half root 3. So a half and minus half root 3 and half root 3 and a half here. Sure, that's right. Okay, good. So we're going to simplify this. We will do row and column. And for those two, that's going to give us half root 3. And next, we do row and this column. And this two will give us a half. Next, we'll do this row and this column. And this two will give us a half. And lastly, this row and this column will give us minus of a half root 3. So this is what we're having for AB. So that is the transformation that is taking triangle DEF onto triangle PQR. So we know that the area of the image, that's triangle PQR, should be equal to the determinant of the transforming matrix AB under modulus times the area of the original triangle, that's triangle DEF. Now the determinant of AB, let's find the determinant of AB. So I'll move this down a little. For the determinant of AB, that's going to be the product of these two, which will be minus 3 over 4. And that's going to be minus the product of these two, which is a quarter. And this actually gives us minus 1. Alright. So essentially, we're saying that the area of triangle PQR is equal to mod of minus 1 times the area of triangle DEF, which will mean that the area of triangle PQR is equal to the area, here's supposed to be an A, of triangle DEF. So that's how we prove it. Okay, that's how we show that the areas are the same, therefore shown. Let's go on to part D. Find the matrix which transforms triangle PQR onto triangle DEF. So triangle PQR onto DEF, the matrix which transforms. So remember, we have triangle DEF giving us triangle PQR under the transformation AB. So the reverse, that is for triangle PQR to give us triangle DEF, should be AB inverse. Okay, so essentially what they want us to find is the inverse of AB. Alright, which will be AB inverse will be equal to 1 over the determinant of AB, and we got the determinant of AB to be minus 1, so it's just 1 over minus 1 off. And for the elements in AB, alright, this is AB right here, we are going to switch positions for this two, so we'll be having minus a half root 3 and half root 3 here, and then we will change the signs for these two, so we'll be having here minus a half and minus a half. Now they're being multiplied by the minus 1 outside, so the matrix will be half root 3, a half, and minus of half root 3. So this is the matrix which will do the reverse, which will transform triangle PQR onto triangle DEF. Next we go on to part E. It says, find the equations of the invariant lines through the origin of the transformation in the xy plane represented by AB. Alright, so the matrix AB is this matrix that we have right on here. So I'm going to copy it and I'm going to paste it down here. So that's the transforming matrix in this particular case. Alright, so we have this matrix AB, and it is going to transform some points on the object, giving us an image, okay, x dash y dash. Alright, so if we multiply row and column, we will come up with a half root 3 of x plus half y being equal to x dash and half x minus half root 3 of y being equal to y dash. Now since we are talking about the lines passing through the origin, it means that y is equal to mx is their form. Alright, so it therefore means that we can substitute mx for y, so that we have half of root 3 of x plus half of mx is equal to x dash and half x minus half of root 3 of mx is equal to y dash. Again, we're going to consider that on the image the lines since they are invariant and they're passing through the origin, y dash should also be equal to m of x dash. So we're going to say for y dash, that's half x minus half of root 3 of mx. That's y is equal to m of x dash, which is half root 3 of x plus half mx. So that's what we are having right here. So all the terms are divisible by x, so we're left with the half minus half root 3 of m equals to, expanding the brackets, that will be half root 3 of m plus half m squared. Now I'm going to multiply all the terms by 2, so each term by 2, and we'll be having 1 minus root 3 of m is equal to root 3 of m plus m squared. And if we rearrange, we'll be having m squared plus 2 root 3 of m minus 1 equal to 0. And if we solve this equation, I'll use my calculator, we will get the values of m coming out as m is equal to 2 minus root 3 and minus 2 minus root 3. So these are the two possible values of m. So therefore, the invariant lines through the origin will be y is equal to 2 minus root 3 of x and y is equal to minus 2 minus root 3 of x. So that's the answer right here to this particular question, and that's how we do it. Let's go on to the next question. On number 5, they say the curve C has polar equation r is equal to ln of 1 plus pi minus theta for values of theta ranging between 0 and pi. So on part A, sketch C and state the polar coordinates of the point of C furthest from the pole. Alright, so we are going to make use of a table of values, and I am going to have intervals within the range 0 to pi, which are intervals of size a quarter pi. So it's 0, a quarter pi, half pi, 3/4 pi, up to pi. So I'll have those values in the table, and I'm going to substitute each one of these values into the equation r is equal to ln of 1 plus pi minus theta. And when we do, when theta is 0, r will come out as 1.4 to 1 decimal place. When theta is a quarter pi, we get that r will be equal to 1.2. When theta is half pi, r will be 0.9. When theta is 3/4 pi, r will be 0.6. And when theta has a value of pi, r will have a value of 0. And we're going to plot these points on our polar plane, and we can see that the graph comes out like this. So I'm going to put the graph right on here in this space. So this is theta equal to 0, and we have the pole right here. I'm going to extend the pole just a little, but the pole is here. So the graph comes out like this according to what we had in the sketch. Alright, now the question says we should state the polar coordinates of the point of C furthest from the pole. Now the point furthest from the pole should be this point here, and that's when theta is equal to 0. So when theta is equal to 0, r will be ln of 1 plus pi, and theta will be 0. So these are the coordinates of the point furthest from the pole. Let's move on to part B. So it says, using the substitution, u is equal to 1 plus pi minus theta, or otherwise, show that the area of the region enclosed by C and the initial line is half of 1 plus pi ln 1 plus pi of ln of 1 plus pi minus 2 plus pi. All right. So this is integration by substitution. We've been given the substitution. U is equal to 1 plus pi minus theta, which means that du by the theta is equal to minus 1, which means that in place of d theta, we can put minus du. We can also consider the limits, okay, theta and u. According to the question, original question, the limits are 0 and pi. So 0 and pi. All right. So since u is equal to 1 plus pi minus theta, when theta is equal to 0, u will be 1 plus pi or pi plus 1. And when theta is pi, u will be 1. So we have 1. All right. So we know that area is found by the integral from alpha to beta of half r squared with respect to theta. And in this particular case, we will be having, okay, I want you to take note of the fact that this was the lower limit and upper, but when we do use the substitution and the sign change, this is now the upper limit and this one is the lower limit. So to account for that, I'll put a minus, okay? And the half, I'll factor it out in the integral from 1 to pi plus 1. And now of r squared. Now, from the original curve, r is ln of 1 plus pi minus theta. So r squared should be ln of 1 plus pi minus theta. But remember, 1 plus pi minus theta is u. So it's just ln u squared of d theta. But in place of d theta, we put minus du according to this. Okay. So we essentially have a half of the integral from 1 to pi plus 1, all right, of ln u squared with respect to u. Okay, so this is what we have. So we're going to use integration by parts here. So we're going to say that's integration by parts. Right, so we're going to say let u be equal to, okay, I'm going to use different colors so that there's no conflict. Let u be equal to, so I don't want you to confuse it with this u, okay? It's just for the sake of us applying the integration by parts formula. So u is ln u and dv by dx be ln of u again. It's a product, remember? So du by, let's just say du by small du. This is small du, okay, is 1 over u. And here we'll get v to be, if we integrate ln u, we get u ln u minus u. Okay, now carrying it on, like from here, I'll just copy this and place it down here. Okay, like this.
Wait, can you explain the integration part?
Okay, of ln u.
Yeah.
Okay, all right. So you need to know that when you're integrating ln, okay, ln x with respect to x, you do by parts again. You say let u be equal to ln x and dv by dx be equal to 1 because ln x is 1 ln x. So du by dx is 1 over x, and v, integrating 1, we get x. So by parts, it will be integral of ln x with respect to x is uv, which is x ln x, minus the integral of v times du by dx. So 1 over x times x is 1. So basically, it's like we are integrating 1 with respect to x. So it's x ln x minus integrating 1 is x. So if you integrate ln x with respect to x, you get x ln x minus x. So that is the same thing here. If we integrate ln u, we get u ln u minus u.
Okay, I get it.
Okay. All right, so this is going to be equal to, by parts, half of uv. We do these two, which would be u ln u minus u of ln u, u ln u minus u of ln u, okay? And the limits are 1 and pi plus 1, and that's minus the integral from 1 to pi plus 1 of the product of these two, which will be 1 over u times ln u is ln u. So it's essentially ln u minus 1. All right. So it's like we're integrating ln u minus 1 with respect to u. So this is essentially a half of u of ln u squared minus u ln u with the limits 1 pi plus 1 minus integrating ln u is u ln u minus u minus u. So essentially we have minus 2u inside from 1 to pi plus 1. All right. We can even combine this into, okay, we have a half outside. We shouldn't leave that out. And we can combine the whole thing into u of ln u squared minus u ln u minus u ln u is minus 2 u ln u, and minus of minus 2 u, it's plus 2u and 1 pi plus 1. Okay, so we are saying from here, we substitute 1 plus pi, so it's a half, okay, of pi plus 1 of ln of pi plus 1. Okay, it's squared, so I'll put another ln of pi plus 1. And that's minus 2 of pi plus 1 of ln of pi plus 1 plus 2 of pi plus 1. All right, and that's minus. Now substituting 1 into this whole thing. This becomes 0, this becomes 0. And here we'll be having plus 2. So actually it becomes minus 2 since we are subtracting. All right, I'll close bracket. All right, now I'll multiply half into the whole bracket. We'll be having, all right, pi plus, actually half of pi plus 1 ln of pi plus 1 squared. So that's like of ln of pi plus 1. And that's minus pi plus 1 ln of pi plus 1. And that's going to be plus pi plus 1. All right. And that's minus 1 because it's being multiplied by a half. All right. So essentially we have, I'm going to factor out a half of pi plus 1 of ln of pi plus 1. Okay. So if I factor it out on here, what will remain is ln of pi plus 1 minus, if I factor out this thing on here, we will just be left with a 2 minus 2 close bracket. And this pi plus 1 minus 1 is pi. And I'm sure that's the exact thing they have that they want us to prove, isn't it? Yeah?
Yes.
It is. So that's exactly how we do it right on here. Okay, what do you think of this?
I just don't like polar coordinates. It's annoying.
Yeah, there's a lot of things to do, especially the integration part. So a little bit more practice is required. Now, on part C, they say, show that at the point of C, furthest from the initial line, 1 plus pi minus theta of ln of 1 plus pi minus theta minus tan theta is equal to 0. Okay. All right. So we're talking about the point furthest from the initial line, and that's when dy by d theta is equal to 0. So we have to express the equation in the form y in terms of theta. So r is equal to ln of 1 plus pi minus theta is the original equation. And we know that y is equal to r sine theta. So essentially, this leads to r being y over sine theta. So therefore, y over sine theta is equal to ln of 1 plus pi minus theta. So y is equal to ln of 1 plus pi minus theta of sine theta. So when we do dy by d theta, it's a product sine theta times the derivative with respect to theta of ln of 1 plus pi minus theta, all right, plus ln of 1 plus pi minus theta times the derivative with respect to theta of sine of theta. Okay, so that's sine theta of differentiating this will give us minus 1 over 1 plus pi minus theta. And that's going to be plus ln of 1 plus pi minus theta of cos theta. Now remember, all this is equal to 0. Now we're going to multiply both sides by this, by 1 plus pi minus theta, all the terms. So we will be having minus of sine theta plus 1 plus pi minus theta of ln of 1 plus pi minus theta cos theta equal to 0. And we're going to divide all the terms by cos theta. And when we do that, we'll be having minus tan theta here, all right, plus 1 plus pi minus theta of ln of 1 plus pi minus theta. These two cancel, equal to 0. Now, that's what they want us to prove, isn't it? That's it. Let's just rearrange. Therefore, this leads us to having 1 plus pi minus theta of ln of 1 plus pi minus theta minus tan theta equal to 0. Okay, and that's shown. All right. So now that we have shown this, okay, I'll say here shown, we will then go on to verify that this equation has a root between 1.2 and 1.3. So we can just say, do we have space? Not anymore. Let f of theta be equal to 1 plus pi minus theta ln of 1 plus pi minus theta minus tan theta, and then we find f. They say which values, 1.2 and 1.3. F of 1.2 equals, and f of 1.3. All right. Okay, did you
I
do
have the
this?
answers.
Okay,
Yeah,
yes.
I have the answers.
Okay,
It's,
what do we get for f of 1.2?
for 1.2, it's 0.602.
And 1.3?
Then 1.3 is negative 0.634.
So there's a sign change, right?
Yes.
Which means that there is a it actually means that there's a root between those two, between 1.2 and 1.3. So that's how we do this question. All right, so let's look at this question here. It says, let A be a positive constant. So on part A, the curve C1 has equation y is equal to x minus a over x minus 2a. Sketch C1. All right. So here we want to make a sketch of this graph, and we're going to consider a few important things. Firstly, we need to know what the asymptotes are. So for the vertical asymptote, we find that by equating the denominator to 0. So we'll say that x minus 2a is equal to 0. So x is equal to 2a. Now, we also have a horizontal asymptote. All right. Considering that the degree of the numerator is equal to the degree of the denominator in this particular case. So to get the horizontal asymptote, it will take the form y is equal to the ratio of the coefficients of the leading terms. The leading term for the numerator has a coefficient of 1, and the leading term in the denominator has a coefficient of 1. So 1 over 1 is 1. So y is equal to 1 is the horizontal asymptote. Next, we are also going to look at the intercepts. All right. For the intercepts, we're going to say when x is 0, what is y? And when y is 0, what is x? All right. So when x is 0 here, we will get y to be a half. All right. So a half. And when y is 0 here, we will get x to be a. All right. So essentially, these are the things we need, and we can now make a sketch. So I have the axis. This is the vertical axis, and this is the horizontal axis. And with the origin here, y-axis, x-axis. All right. The vertical asymptote is x equal to 2a. So I will have the vertical asymptote being a vertical line going like this, and it intercepts at 2a. Then the horizontal asymptote is at 1. So a horizontal line going like this. So here we have a 1. All right. And now we will also need to just understand the behavior of the graph about these asymptotes, especially the vertical asymptote. Okay, so we can consider a value that is, say, greater than 2a. We can take maybe 3a. When x has a value of 3a, substituting it into this, we'll be having 3a minus a over 3a minus 2a, and we get y to have a value of 2, and 2 is positive. And if 2 is positive, it means that the graph for a value that is greater than 2a will be coming from above. And when x is a value that is less than 2a, say for example, half a. So when x is equal to half a, if we substitute half a here, half a here, and half a here, we will get 0.5a over minus 0.5a, which is minus 1, essentially, which means the graph for a value that is less than 2a is coming from down here. All right. We have also established that the graph has intercepts. That's when y is equal to a half. So maybe here, and at x equals to a, which is somewhere here. All right. So this is basically what we have. So the graph should come out like this. So like this, and this part should come out like this. So this is how the graph should be like. All right, let's move on. Now we are on part B, I think. On part B, the curve C2 has equation y is equal to x minus a squared, x minus a over x minus 2a all squared. The curve C3 has equation y is equal to mod of x minus a over x minus 2a. So on B part 1, find the coordinates of any stationary points of C2. Okay. So we are talking about C2 in this case, which has this equation, and we're talking about stationary points. So we are saying that for y being equal to x minus a over x minus 2a all squared at the stationary points. So we don't know how many there are, okay? But we know that dy by dx should be equal to 0. So I'm going to say let u be equal to x minus a over x minus 2a, which therefore means that y is equal to u squared, because this is u, so y is u squared. This will give us dy by du coming out as 2u. All right. And here we'll be having du by dx being x minus 2a times the derivative with respect to x of x minus a minus x minus a. Right. I'm going to move this so that we have a bit of space. All right. Of the derivative with respect to x of x minus 2a. All right. And that's over x minus 2a squared. Okay. So this will give us, differentiating this part, we get 1. So we have x minus 2a minus x minus a of, differentiating this part, we get 1 as well. And it's over x minus 2a squared, okay? Which simplifies to here, x minus x is 0. Then minus 2a minus a is minus a. So we have minus a over x minus 2a squared. So applying the chain rule, we can say that dy by dx is equal to dy by du by du by dx, which will therefore be dy by du is what we got right here to be 2u. So it's essentially 2 of u, and u is this x minus a over x minus 2a. And that's times du by dx. Okay, du by dx is what we just got right here, which is minus a over x minus 2a squared. And remember, dy by dx is equal to 0 at the stationary point. So essentially, we have minus 2a of x minus a over x minus 2a squared, actually cubed now, equal to 0, which will lead us to having, if we multiply both sides by the denominator, minus 2a of x minus a equal to 0. And with that, if I just resize this a little, with what we have here, we can say that x is equal to a. Now, when x has a value of a, okay, we can substitute a into the original equation of the curve. And when we do, if we put a here and a here, a minus a is 0 on top. So therefore, we get y to be 0. So for the coordinates of the stationary points, we're saying that when x is a, y is 0. So this is the answer. Thus, remember the question wanted us to find the coordinates of any stationary points. So we have one stationary point on C2, and it happens at A0. It's at A0. Let's move on to B2. On B2, they say, find also the coordinates of any points of intersection of C2 and C3. All right. So remember, C2 is the curve. Y is equal to x minus a over x minus 2a all squared. And C3, okay, for C3, we got it to be the modulus graph, all right? So it's essentially y is equal to x minus a over x minus 2a and the modulus, okay? So the point of intersection is where these two curves intersect, where mod of x minus a over x minus 2a is equal to x minus a over x minus 2a squared. So if we use the plus or minus method, we'll be having x minus a over x minus 2a being equal to x minus a over x minus 2a all squared. Okay, I'll just put the squares like this, which is still okay. Or x minus a over x minus 2a being equal to minus of the same x minus a squared, x minus 2a squared, basically. All right. So if we multiply both sides by x minus 2a squared, this side again by the same x minus 2a squared, here we will be getting, dividing here, x minus a of x minus 2a, and that's equal to, these will cancel, so that's x minus a squared. Expanding the brackets, we get x squared minus ax. Actually, it's minus 3ax. All right. And that's plus 2a squared being equal to, expanding this, that's x squared minus 2a plus a squared. Actually, that's minus 2ax plus a squared. So, subtracting x squared from both sides, we will get 0. So we'll be having minus 3ax plus 2ax being equal to a squared minus 2a squared. So that's going to be minus ax, all right, being equal to minus a squared. Dividing both sides by minus a gives us x to be a. On the other part, we're going to multiply both sides by x minus 2a squared, and this side again by the same. And when we do, we will be having on the left side x minus a of x minus 2a being equal to minus of x minus a squared. So expanding the left side, we get x squared minus 3ax plus 2a squared being equal to minus of x squared minus 2ax plus a squared. So that's x squared minus 3ax plus 2a squared is equal to minus x squared plus 2ax minus a squared. Rearranging, if we take everything that's on the right to the left side, we'll be having 2x squared minus 5ax plus 3a squared equal to 0. And we can actually factorize this. We'll be having 2x here and x. And for factors of 3a squared, we can have 3a and a, minus and minus. So we have factorized this. So the possible values of x will be 3 over 2 of a, or x is equal to a, which we got already. Okay, so x is equal to a. So the question, remember, says we should find the coordinates of any points of intersection of C2 and C3. So C2 and C3 intersect when x is a value of 3 over 2 of a and a certain y value, and a and a certain y value. Now, for when x is equal to a, we have already established that when x is a value of a, y is 0, okay? So this one is good. And then when x is equal to 3 over 2 of a, if we go to one of the graphs, C2 or C3, let's go to C3, okay? So here, if x is a value of 3 over 2 of a, we'll be having y being equal to modulus of 3 over 2 of a minus a over 3 over 2 of a minus 2a, which is essentially on top 0.5a over minus 0.5a, which is mod of minus 1, which is essentially 1. So the y coordinate here should be 1. Okay, so what we have now is the answer. Now on part C. On part C, they say, sketch C2 and C3 on a single diagram, clearly identifying each curve. Hence, find the set of values of x for which the squared graph is less than or equal to the modulus graph. Okay. All right, so let's look at it. I'm just going to take the graph that we had earlier because we will just need to modify it. We'll need to modify it. Okay, so I am going to paste it down here. All right, so the graph that I have here is the graph we drew originally, which was the graph of y is equal to x minus a over x minus 2a. All right. Now, we want to sketch C2 and C3 on the same plane. So we want to start with the graph of C2. Now, C2 is the squared graph, okay? So let's start with that. So C2 is y is equal to x minus a over x minus 2a all squared. All right, so for the squared graph, you know how if you square a function, all the parts of that function which are negative, remember if you square a negative number, it gives you a positive result, okay? And it will be a squared result, so a higher, bigger value than you originally had, and positive as well. So we are going to say that for all these values that are along this line, they will come out being positive. So we will be having the graph like this. So it's like we've squared the y values here. So the x values remain the same. Okay. Next, if we consider this line segment here, all the points on this original graph, after squaring, you can see that all the points that are on this particular line segment are values that are between 0 and 1. And if we square them, they become even smaller. Okay. If you square a number between 0 and 1, it becomes smaller, okay, because it's a bottom heavy fraction. So we're also going to have the points come down like this, okay. Next, if we consider this line segment for the squared graph, these values, all the values that are on this line are actually greater than 1. And if you square a value that is greater than 1, it becomes bigger. So the y values become bigger. So we expect the curve to be higher than the original. So the graph in red that I've drawn is the squared graph. So I'm just going to do it this way. Red is for the curve C2. So it's y is equal to x minus a over x minus 2a all squared. I'm going to use black for the graph C3. And for the C3 graph, that's y is equal to mod x minus a over x minus 2a, like this. So for the modulus graph, the simple thing we need to do is to reflect this line segment, okay, the part that is negative, all right? So essentially, it will come out like this. It's been reflected, so more like this, all right? And I'm trying to make sure that these two graphs intercept at this particular point as well as at this particular point, because already we had figured out that there are 2 points of intersection. All right. So those are the 2 points of intersection, basically. So this is how the graphs will be like. C2 is the graph in red. C3 is the graph in black. And the part that is below the x-axis is no longer needed. So this is what we will be having here. Now, the question says, hence find the set of values for which the squared graph is less than the modulus graph, less than or equal to the modulus graph. Less than means vertically below, all right? So relative to the points of intersection, we have two of them, this point of intersection and this point of intersection. So relative to those 2 points, you can see here that the squared graph, which is in red, is vertically below the black graph, which is C3, for all values that are less than this point of intersection, which is when x has a value of 1.5, okay, 3.2a. For all values that are to the left of that line, the squared graph, which is the one in red, is vertically below the modulus graph, which is the one in black. So we are saying that the solution is values of x that are less than or equal to that x value, which is 3/2 of a. So that's the answer right here. And that's how we answer this particular question. So let's take a look at question number 7. It says the points A, B, C have position vectors minus 2i plus 2j minus k, minus 2i plus j plus 2k, and minus 2j plus k, respectively, relative to the origin or. So on part A, find the equation of the plane ABC, giving your answer in the form ax plus by plus cz equal to d. All right, so basically, it's like we have a plane, all right? And for this plane, there are points, okay? 3 points, A, B, and C, and they want us to find the equation of the plane. So in order for us to find the equation of the plane, we will first need to find the vectors A, B, and AC. So basically any 2 vectors on the plane so that we can be able to use vector product to find the common perpendicular, which will be the normal, okay? So essentially here I'll be saying for AB, that's OB minus OA, which is minus 2i plus j plus 2k minus OA, which is minus 2i plus 2j minus k. So this is going to give us minus 2i plus 2i, that's 0. Then j minus 2j, which is minus j. And we will also be having 2k minus k, which is 3k. So plus 3k. So that's AB here for us. So now that we have AB, let's also find the vector AC, all right? So for the vector AC, we'll be saying that's OC minus OA. Now OC is minus 2j plus k, and that's minus 2i plus 2j plus k, actually minus k it is. So minus k like this. So we'll be having here 2i, then minus 2j, minus 2j is minus 4j, then k minus k should be 2k. So it's plus 2k like this. So in order for us to find the normal n, we have to do vector product. So say here I, j, k, all right? And we'll be having, for the first one, minus j plus k. So that's basically 0, minus 1, 3. And for this one, that's 2 minus 4, 2. All right. So what this is going to give us is we will close out these and we will do minus 2 minus minus 12, which will give us 10. Okay, so that's 10i that we will get from here. All right. And then we will close out this middle one, and it will be minus of 0 minus 6. So it's minus 6, and we'll put a minus on it. Remember, it's plus minus plus. So it will eventually come out as 6. So 6j here. Next, we will close out these, and we will do 0 minus minus 2. So we just get 2 from this. So that's plus 2k. So that's what we're getting here to be the normal to the plane. We'll also need the distance d, which is found by a dot n, which will be a is any point on the plane, which in this case is this point. In vector form, column vector form, that's minus 2, 2, and minus 1. So we have minus 2, 2, and minus 1 dot n, which we take from this. That's 10, 6, 2. And this will give us minus 20 plus 12 minus 2. And this will give us right here minus 10, basically. All right. So for the equation of the plane, it will be 10x plus 6y plus 2z, taking it from this, and that's equal to minus 10. And we can simplify it by dividing all the terms by 2. 2 give us 5x plus 3y plus z is equal to minus 5. So this is what we are getting right here. Let's move on to part B. On part B, the question says, find the acute angle between the planes OBC and ABC. So let's start with the normals, all right? Because to find the angle between two planes, we use cos theta is equal to n1, n2, which are the normals, okay? The dot product of the normals over mod n1, mod n2, all right? So we'll need to find n for OBC, all right? The normal to the plane OBC. Now, the plane OBC has vectors OB and OC on it. So we'll do vector product for OB and OC. All right. So I will say IJK. All right. And we'll be having for OB, that's minus 2, 1, 2. So minus 2, 1, 2. And OC, that's 0, minus 2, 1. So we have 0, minus 2, 1 right here. All right. So if we do this, we will be getting here, if we close out this, we will be having mod of 1, 2, minus 2, 1. Actually, let me just do the workings right away. So we're saying that if we close out I, then we'll be having 1 minus minus 4, which is 1 plus 4, so that's 5. So we have 5i here. So 5i, and then we close out the middle, and we'll be having here minus 2 minus 0. So basically minus 2, but minus of minus 2 is 2, since we should put a minus at the middle. So we'll just be having here 2j. And then lastly, we close out these, and we do 4 minus 0. So that's just 4. All right. So we'll say here plus 4k. So that's the normal to OBC. All right. The normal to ABC, the plane ABC, we already have it. Okay. The normal to the plane ABC. The plane ABC is the one we're working with. And we got the normal to be this, which is actually proportional to, if we reduce it to lowest terms, if we reduce it, dividing by the common 2, it's like 5i plus 3j plus k, basically, all right? So 5, 3, 1, okay? 5i plus 3j plus k, all right? So these are the two normals. So we'll do dot product. Okay, we'll say here, therefore, cosine of theta will be equal to the dot product of 524 and 531. All right, and that's going to be over the square root of 5 squared plus 2 squared plus 4 squared times the square root of 5 squared plus 3 squared plus 1 squared. Okay, so on top, we'll be having 25 plus 6 plus 4, which is 35. And at the bottom, we'll be having root of 35 times root of 45. So essentially, we have 35 over the square root of 1575. So to get theta, we'll say it's a cos of 35 over the square root of 1575, which will give us, to one decimal place, 28.1 degrees. So 28.1 degrees is the answer right here. So that's how we do it right here. Now let's move on to part C. So on part C, it says the point D has position vector Ti minus j. So given that the shortest distance between the lines AB and CD is root 10, find the value of t. All right, so here we're talking about the shortest distance between two lines. And for this, we will use the formula D is equal to A1 minus A2 dot B1 cross B2, and that's over mod of B1 cross B2. And we will need the absolute value of this. And this works for two lines. R is equal to A1 plus lambda B1, and R is equal to A2 plus mu B2. So in our case, we have two lines, AB, and the line AB has equation R is equal to A. Okay, let's take a point on the line AB. Let's take the point A. That's minus 2, 2, minus 1. So we have minus 2, 2, and minus 1. And that's going to be plus lambda of the direction of AB, the direction vector of AB. We got it here. That's 0, minus 1, 3. So I'll have that. 0, minus 1, and 3. And for the line CD, the line CD is R is equal to, and we can take any point on the line. Let's take the point C. The point C is 0, minus 2, 1. So we have 0, minus 2, 1. All right. And that's going to be plus mu of, and now we need the direction vector of CD. So I'll move this a little up. So for CD, that's OD minus OC, and OD is here. That's T minus 1, 0, and that's minus OC, which is 0, minus 2, 1, which will give us T, 1, and minus 1. So we have here T1 and minus 1. All right. So we can now say for A1 minus A2, that's minus 2, 2, minus 1, minus 0, minus 2, 1, and that gives us minus 2, 4, and minus 2. Then for B1 cross B2, this is B1, that's 0, minus 1, 3, cross T1 minus 1. And this gives us, if we close out these elements, we get 1 minus 3, which is minus 2. So we have minus 2 here. Then we close out the middle ones. So that will be having 0 minus 3t. So that's minus 3t, but we put a minus on it to make it 3t. Then we close out the last ones. So that's 0 minus minus t. So we get here t. So that's the cross product. And lastly, we'll need the modulus of that, which will be the square root of minus 2 squared plus 3t squared plus t squared, which is the square root of 4 plus 90 squared plus t squared. So that's 10t squared. All right. So with what we have, we can now find d. Remember the formula we're using? Let me just put it on the side. So basically, that's going to be d is equal to, all right, under modulus, the dot product, a1 minus a2, that's minus 2, 4 minus 2 dot, minus 2, 3t and t. And that's over the square root of 4 plus 10t squared, like this. All right. So this will give us, actually the question says this is equal to root 10 because we're looking for the value of t. So we'll equate this to root 10. So basically we have 4 plus 12t minus 2t over the square root of 4 plus 10t squared is equal to root 10. All right. And I'll multiply both sides by the denominator. So we have 4 plus 10t is equal to the square root of 10 or 4 plus 10t squared. I'll square both sides. So we have 4 plus 10t squared is equal to 10 or 4 plus 10t squared. So that's 16 plus 80t plus 100t squared is equal to 40 plus 100t squared. Subtract 100t squared from both sides. So we have 80t is equal to 40 minus 16, which is 24. So t is equal to 24 over 80, which is 0.3. So that's how we find the value of t. T is 0.3 in this case.